Well, the way to understand this question is to use what we just did. We know, either by path independence or by Kirchhoff's loop law, that the potential difference across resistor R1 is the same as the potential difference across resistor R2. And so we can write that down using Ohm's law to express those two potential differences. And then since we know that R2 is the larger resistance, then for this equation to balance, I1 must be the larger current, and so the answer is B. Remember what's going on with energy in a circuit like this. Chemical energy is being converted into electric potential energy in the battery, and all of that electric potential energy is being converted to thermal energy in the resistors. And so the amount of energy being converted in the battery must equal the total amount of energy being converted in the resistors. And so let's look at how that plays out. A unit analysis is enough. Remember that epsilon represents a work per unit charge, and this current represents a charge per unit time. And so that means that if you just take epsilon times I, that is a work in joules per coulomb times an amount of charge per unit time, and so that is joules per second, which is just watts. And so this is the power in the battery, which is just the rate of energy conversion there. Similarly, in a resistor, you have a current, and that is a charge per unit time, which is falling through a potential difference, delta VR. And that delta V is just IR. And so we have this expression for the power in a resistor. In other words, the rate at which energy is being converted from electric potential energy into thermal energy. So look at what that says about this circuit. We have epsilon I is the power in the battery. And in the resistors, I1 and I2 are just I, which we could write this way. But we already know from the loop law that epsilon is equal to IR1 plus IR2, and so that is I epsilon. And so we see that the total power in the resistors is the same as the power in the battery. And this is always true for any resistor circuit. I'll leave it to you to show that this works the same way for parallel resistors. I want to finish up by looking at a circuit that is less simple, but still quite simple. So this looks a little complicated because it's got a battery and a capacitor and a resistor. But note the way we're going to use it. First, we're going to close switch 1. And so that is going to charge the capacitor. And we've talked about that process. We know how it turns out. We know in particular that eventually the capacitor will be fully charged so that the potential difference across the capacitor is equal to the EMF of the battery. And so in particular, that means there will be a fully charged Q, which I'm going to call Q0, which is just C epsilon. Then we open switch 1, so the battery might as well not exist now, and close S2. And what will now happen is that the capacitor will discharge through the resistor. Now remember, what that means is that negative charge, electrons, are going to flow off of the negative plate around to the positive plate through the resistor. But we are going to think instead using conventional current, and so that is going to go in the opposite direction. And so we are talking about a current which now flows around this as the capacitor discharges. But notice what happens. Because the potential difference across the capacitor depends on the amount of charge on it. And this current represents charge flowing off of it. In fact, this current would be the negative derivative of the charge on the capacitor with respect to time. Why negative? because that charge is decreasing, and that is being registered here in our sign convention as a positive current. So that means, since the potential difference here is decreasing, the potential difference across the resistor is decreasing, and it is the potential difference across the resistor that determines the current. So the current must start rather large and decrease with time. Well, that sounds complicated, and it's a little bit complicated, but all we have to do is write Kirchhoff's loop law. So I'm going to again think in terms of walking around a loop, and I'll do this loop. And so I know that as I walk through the capacitor, the potential is going to go up by Q over C, where I'll note that this Q is a function of time. And then as I walk through the resistor, it will drop by IR, but I'll note that that I is also a function of time. And that's the whole loop. So now let's solve this. Notice that since that I is dq by dt, or negative dq by dt, I can write this all this way. And that is a differential equation. I'm going to just rearrange it a little bit, which perhaps looks a little intimidating since most of you haven't learned differential equations. But note, again, this is a simple one, just like the one we met last term for simple harmonic oscillators. It's a different equation, and it has a different solution, but we can argue the solution in roughly the same way. Q is apparently a function of time, and it is a function where when you take its first derivative, you get back the original function times a constant. Well, we know what kind of function does that. Q must be an exponential. So when time is 0, the exponential is 1, and Q will be Q0. And the constant must be negative 1 over RC. And so there is our solution. And in particular, that tells us that the charge on the plates is decreasing exponentially. And remember that the current is just the negative time derivative of the charge. And that comes out also to a negative exponential. RC, I will leave it to you to show, has units of time. It has to, because the argument of the exponential has to be unitless, and so we often call it the time constant for this RC circuit, tau.